All right, quite often in probability scenarios, you are picking or drawing without replacement. This is a very common occurrence in the real world. Think back to our previous unit when we were picking people to go in the dorm room and we were simulating whether it was likely or not to pick all varsity players. And remember, we had to ignore repeats because once we picked a person, that person was no longer able to be chosen. And that's what's happening when you draw without replacement. Once you pick and you don't replace it back in the total, then there's one less object in that total sample space, and that will alter your probability, okay? So basically it's just an example of non-independent events. The picks are not independent. But like when we roll a die, you can roll a 1 again if you got a 1 on the first one. So that would be independent. But if you couldn't roll, if the 1 came off the die somehow, which it can't, then the likelihood of you getting another 1 would change. So that would be not independent. So sampling without replacement means that once one individual is drawn, it does not go back into the pool. We often sample without replacement, which doesn't matter too much when we're dealing with a large population. So, for example, you're going to have a situation where you're picking M&Ms from a large supply. And you're told that in the problem. And what they're basically telling you there is to assume independence. So I want you to kind of think about like all the M&Ms in the world. You know, your brain probably can't even process that, but all the M&Ms that are out there right now. And I want to know what's the probability or the proportion of all M&Ms that are red. And let's say it's 10%. 10% of all M&Ms are red. And I open a bag of M&Ms and I pick a red out of my bag and I eat it. So now is there no longer 10% red M&Ms out in the world because I just ate one? I mean, technically you did just reduce the population and reduce the number of reds, but in the whole big scheme of things, there's still 10% red M&Ms in the world. You did change the proportion, but you changed it by such a far out decimal place that it's really virtually still just 10%. So we assume independence, or you could say that their picks are virtually independent when you have a large supply, okay? However, when drawing from a small population, we need to take note and adjust probabilities accordingly. Drawing without replacement is just another instance of working with conditional probabilities, and it's also the same idea of working with non-independent scenarios. Non-independent scenarios. Okay? For example, if you can imagine a bowl of M&Ms and I've got one red and I've got 2 blues and 2 greens. This is a small bowl of M&Ms. And I want to know what's the probability of me picking a red, not replacing it, and then picking another red. Well, the probability of picking the first red was 1 out of 5. The probability of picking the second red, remember our formula is you can multiply, but you got to multiply by the probability of picking the second one knowing you already picked one. Well, guess what? That changes it to 0. I just picked the only red out. Probability of my second pick being red? Can't happen. So notice the probability of picking red changed on the second red from 1/5 to couldn't happen at all. And that's what that formula is. When we use our multiplication rule, the probability of A and B is probability of A times probability of B knowing A occurred. That second probability might change because of this first one occurring. You and your friend are getting ready for your dorm assignment. There are 12 total rooms available, 3 in the gold hall, 4 in silver hall, 5 in wood. What is the probability that you and your friend both get gold rooms? Both. That's an and, that both word. The most desirable dorm on campus. So we want to know what's the probability someone gets picked for gold or you get picked for gold and your friend gets picked for gold. We need both to occur. This is a small population. We're only talking about 12 rooms. Out of those 12 rooms, 3 of them are in Gold Hall. So the probability of one person getting picked to be in the Gold Hall is 3 out of 12. We're going to multiply that by the probability of the second event, but don't forget it's conditional. Now what's the probability of the second person getting gold knowing the first one already got one of the rooms? So now there's only 2 rooms left in the Gold Hall, and on top of it there's only 11 rooms left to be picked. So the conditional probability of gold, remember the probability of gold alone was 3/12. But the probability of gold knowing a gold has already been picked. So now you got to take one of those out. That is going to change to 2/11. Because now there's only 2 left and there's only 11 total. So that's what that conditional formula is all about for non-independent events. When we were doing like the red light and the green light, those events were independent. So the second event occurring was still just equal to the probability of that variable, even though the first event already occurred.